all places. It is indeed a great occasion for me to introduce Vinod. He has done his PhD from Massachusetts and later on did his postdoc at various places, including Princeton. And currently he is the professor and chair at the Department of Physics, CCUNY, what is it, Vinod?
Yeah, so City College of New York, which is under the City University umbrella. Yeah.
Yeah, and then he his research interests include, nano and microphotonics, and he's been doing great work in this field. And he is, working towards, he is working towards creating programmable matter, which is based on combining material excitations with light, and calls it half light, half matter quasi-particles. And he is going to talk to us about this and many more things. Over to you, Vinod. And it's indeed a pleasure to listen to you.
Thank you so much, Professor Ananthalakshmi. It's a pleasure to be here, especially with two of my old professors in the audience, Professor Panigrahi and Professor Ananthalakshmi. I learned some of my early quantum optics from Professor Ananthalakshmi, and thank you all for coming. And firstly, I want to apologize for the mistake I made yesterday in my calendar. I somehow messed it up, so I'm really sorry about that, and thank you all for coming. Let me share my screen. Can everyone see my screen?
Yeah, we can see it.
Okay, great. Okay, so then let me just. Okay, and feel free to interrupt me if you have any questions as I go along. It's a longish talk, but we'll see how far we get. I'm going to talk today about, as Professor Ananthalakshmi mentioned, this idea of quasi-particles that get formed by the interaction between light and matter. And specifically in today's talk, I want to focus on this class of materials called van der Waals materials. Some people call it quantum materials as well, where a strong exciton-photon interaction can be realized. And at the very outset, all the agencies that make this funding possible. So I've listed all the agencies that have allowed me to work. So just to give you an idea of this family of materials that we call van der Waals materials. So everyone's heard of graphene. Of course, graphene is the most well-known system because that was the first discovery that led to isolating a whole sort of other materials. But for the purpose of this talk, I will focus mostly on a class of materials called 2D chalcogenides. So these are molybdenum, tungsten sulfides or selenides. And then I'll also talk about some other materials towards the end of the talk. So the reason why these chalcogenide materials became very interesting is like graphene, they are also van der Waals materials, which means that in the plane of the material, they are held by very tight bonds, and between the layers, they are held by weak bonds. So unlike graphene, which is one sheet of carbon atoms, these materials are actually comprised of three layers. There is in this case, a molybdenum atom, and the sulfur atoms will be on either side. So it's actually a three-layer system, but each of this is separated by van der Waals force, which means that you can remove one from the next layer using the well-known and what is now well known as the Scotch tape technique. So you use Scotch tape and you peel it off, and you can get these layers of material. What also happens in these materials is as you go from the bulk form to the monolayer form, you can go from something that is an indirect bandgap material to a direct bandgap material. And this makes it very interesting because if you think about the luminescence properties or the optical properties, just going from two layer to one layer shoots up the photoluminescence by about a factor of 1,000. So in the monolayer limit, you get a lot of intriguing properties. Just from the standpoint of the strength of light matter interaction, you will see that. So this is a graph taken from this paper here. The yellow line is the solar flux. So the pitch of this paper was about making solar cells, but that's not what I'm going to emphasize on. What I want to point out is, let's look at one of these resonances that this material has. So in, for example, molybdenum sulfide. You will see that at around 2.1 eV, it absorbs about 12% light. So now we need to put this in context, because one layer of this material is 0.7 nanometers thick, or 7 angstroms thick. And we are saying that that thin material absorbs 12% light. That's a huge amount of light absorption cross-section that you're seeing here, compared to almost any other material that you can think of. So silicon, which is the most widely used solar cell material, you will need 50 times that thickness, roughly 50 nanometers, to get the same amount of absorption. So it has a huge strength of interaction with light. The other interesting thing is, because you're going from a 3D limit to a 2D limit, the electron and the hole that are in these materials, the flux lines between them, the screening gets modified. The screening is very different. So there is very weak screening outside. And so the screening only happens in the 2D limit. And the result of this is these electron and holes are very tightly bound. And hence they have a very large binding energy. So they have a binding energy on the order of 0.1 to 0.5 eV. Just to give you again a feel for the numbers, gallium arsenide, which is one of the most widely used semiconductor, the binding energy is in the tens of milli electron volt. So almost an order of magnitude smaller or even less. The result of this is that the exciton is very well separated from the quasi-particle band. They are not, so there are, for those of you familiar with excitons, there are two kinds of excitons, or at least two broad kinds of excitons, which are called Frenkel and Wannier-Mott excitons. The Frenkel excitons are what is found in organic materials. They're tightly bound, whereas in the case of Wannier excitons, they are more delocalized. And this is just to show that the wave function is actually delocalized. Because the binding energy is so large, you can actually see excited states. So you can see the Rydberg states of exciton. So you can think of the exciton as a hydrogen atom, and in which case you can see the excited states of these atoms. Now I'll point out why this gets interesting as we go along, which is that, and I think last time when I spoke at the same workshop, we discussed briefly some of the work we had done with these systems, where we showed that if you get to these larger states, then you get more nonlinear interaction. I'm going to skip this. Okay, so now I'm going to just point out the last, but more from an experimentalist standpoint, what makes these materials interesting is also the fact that you can stack these materials one on top of the other like a Lego block. So, and the nice thing is you have all sorts of materials. You have graphene, which is a semi-metal. You have hexagonal boron nitride, which is a insulator. Can I get recording option? I don't know if that question was meant for me, but I saw a message on the chat. Anyway, I was going to say that graphene is a semi-metal, boron nitride is is an insulating material, and then these materials like molybdenum disulfide, tungsten sulfide, selenide, they are all semiconductors. So and then if you stack them next to each other, you can get also the property. So from a pure condensed matter physics standpoint, or working with optics of semiconductors, one big change that has happened is, prior to these materials coming into the field, you always, for pure materials, you always relied on techniques like molecular beam epitaxy, or such highly clean techniques to get high quality materials. So if you wanted to study 2D electron gas and so on, people studied that. But with the emergence of 2D materials, suddenly the gates have opened and anybody can do it. When I say anybody, I literally mean anybody, because you just have to buy a little bit of this crystal or get a crystal from somebody, and then as long as you've got good hands and time to spend in exfoliation, you can create these heterostructures and study them. So you're not limited in the quality of the materials for a lot of the experiments anymore, because these materials are readily available in the commercially, and you can just buy and use Scotch tape and exfoliate it. So just a quick recap of why these materials are interesting. They have, especially the chalcogenide materials, they have a large binding energy, they have a large oscillator strength, they interact with light very strongly. Because of the binding energy being large, you can also see all sorts of complexes, which are more than just an electron-hole pair. So this is an electron-hole pair with an additional electron attached to it, or a hole attached to it, which are called trions. You have the Rydberg states I talked about. And of course, they also have nonlinear properties, and we'll discuss that briefly. And there is also valley polarization, which I won't get into in today's talk. So this is the broad outline of my talk. I'm going to talk a little bit about Rydberg polaritons, interlayer polaritons, and then some strain engineering and for nonlinear response, and then exciton polaritons and correlated materials. So just a quick primer on what is strong coupling and these quasi-particles. So you take a material resonance. The material resonance can be an exciton, charge oscillations, lattice vibrations. You couple that to a photonic resonance, which is given as I show here. And the idea is that the resonances are exactly aligned or they're in resonance. And the result of this is that you get these hybrid states, upper and lower polaritons. And what makes these hybrid states interesting is these hybrid states now have properties of both the material excitation and the photon resonance. So here is a better picture of what goes on here. So you have a cavity, two mirrors, you have a standing wave that gets produced. You put a two-level system inside the cavity. The two-level system interacts with the cavity photons. You have the damping rate of the two-level system. You have the damping rate of the cavity, or the rate at which the photons leak out. And you have a rate at which the interaction happens between the two-level system and the cavity photon. As long as this rate is greater than the damping rates of either the two-level system or the cavity photon, then you get into this regime where you get Rabi oscillations and you get into the strong coupling regime. And so now you can write your Hamiltonian of the whole system as the Hamiltonian of the cavity plus exciton. Exciton is my two-level system here, the electron-hole pair, and the interaction term. So the interaction term is basically this here, which is A dagger B, which is creation of a photon, annihilation of a exciton, annihilation of an exciton, creation of a photon. Sorry, the other way around. Annihilation of a photon, creation of a exciton. And so let's look at these terms here. I'm just going to go through it. So this is my cavity photon, which is this dashed line here. The exciton is almost a flat line. The reason it's a flat line and doesn't have dispersion, while you do know from your Kittel, your textbook, that the excitons also should have dispersion. The reason you don't have a dispersion is because within the wave vectors we are talking about, this is so much more massive than the photon that it will be almost a flat line. You need to go to very large wave vectors before you start seeing any curvature of the exciton. So within the wave vectors where you want to resolve the cavity dispersion, the exciton can be treated as a flat dispersion because it's so much more massive. Of course, when you get into the strong coupling regime, you get at this crossing points, you get new hybrid states, which are called the lower and upper polaritons. Now, a very analogous phenomena happens when you take two harmonic oscillators and you couple them, and you do the normal mode splitting. You get the two normal modes of the system, and those normal modes now, of course, the splitting depends on the coupling strength, the damping rates of the individual oscillators, and so on. So there is a classical analog of this whole process as well. And then you find the solution to the problem. You diagonalize the Hamiltonian. You get the solutions for the polaritons, which look like this, the P and Q that I've written here. So what is interesting about this, if you look at P, the lower polariton, it has a coefficient which is attached to B. And that coefficient is the coefficient that dictates what is the fraction of excitonic component on that polariton. And then this one here is the term that dictates, where CK is the term that dictates the coefficient that dictates how much, how photon-like is that branch. So let's just look at this branch here. Right here at k equal to 0, it is very photon-like because it looks very similar to the cavity photon right here. I go right outside out here, and my lower polariton is very exciton-like. So all that will happen is this xk and ck change in magnitude as I traverse the in-plane momentum of the structure. And this is the k parallel of the cavity. So this is my cavity structure, two mirrors, my material inside, and I'm looking at it as a function of in-plane momentum. And as I look at it, I say that as I go from here to here, I change the fraction, I change the constituents of this quasi-particle, making it going from something that is very photon-like to something that is very exciton-like or matter-like. And then the two eigenstates are given by this, with the plus and minus corresponding to the energies of the upper and lower polaritons. So what makes van der Waals materials specifically interesting is because they actually host all sorts of polaritons. Now, as I mentioned earlier, polaritons don't have to be just excitons and photons. It can be plasmons in graphene, phonons, lattice vibrations coupled to photons, in the case of boron nitride, topological insulators, and so on. Exciton polaritons, where excitons are coupled to photons. There has been predictions of Cooper pair polaritons and Menon polaritons, and so on. And so there's a lot of these 2D materials, or these van der Waals materials, are a nice playground to study a variety of these quasi-particles and their manifestation and in other related phenomena. So the early interest in polaritons was driven partly by the fact that these excitonic component provides you the electronic scatter response nonlinearities, whereas the photonic component provides you the small mass, spatial coherence, long propagation length, and things like that. So you really get the best of the both worlds. So for example, if you take photons or photonic two lasers, they will just go through each other because they don't like to interact with each other. Whereas if you take a polariton system, because it has got the material excitation embedded in it, they do interact with. So the nonlinearities are higher. So that was one early motivation. The other big motivation was driven by the cold atom community. People were very interested in whether you can get condensation of these polariton states. And this was primarily because your temperature at which you get condensation is dictated by the mass of the particles and indirectly the de Broglie wavelength. And it turns out that because the mass of these guys is much lighter than the cold atom system, you should be able to get condensation at elevated temperatures. And in fact, this was the work that was actually driving the early part of the 2000 to 2010. The work in this field was primarily driven by this whole idea of condensation in the system. First demonstrations in 2007, 2008 by multiple groups. And essentially what happens there is you create the polaritons, they scatter, and they create you get a macroscopic coherent state here, which shows all the condensation behavior. Now, sometimes people call them BECs or polariton BECs. One has to be a little careful about that because they're not true BECs, at least most of the experiments done till date, because these are out of equilibrium systems. You have to constantly drive them. The photons are leaking out. So the polariton number is not conserved in this case. And hence, one could talk about it like a condensate. It has all the properties of a condensate, but you have to constantly be driving them. So they are out of equilibrium systems. But nevertheless, they show properties like superfluidity and all of that condensates and vortex, anti-vortex formation, all of that condensates normally do. So here is an example where which has been done just recently in my group, where we don't even need low temperature. This is actually a room temperature data, where instead of taking, there's a slide, I'm going to digress on this one slide. I'm not taking 2D materials. I'm not taking traditional semiconductors. I'm actually taking fluorescent proteins. So these are fluorescent proteins that biologists use for imaging and things like that. And so you can get these from the biologists. And then we encapsulate them between two mirrors. And it turns out these materials have got an incredibly large quantum yield, and they're really pretty robust in most cases. You can get something that looks like lasing, but it's not really lasing because we have not hit the threshold for real photon lasing. So this threshold is actually a threshold where we're actually getting onset of condensation in this system. And so you can see here, this is in momentum space. This is the distribution in momentum space. And then you go to above the threshold and everything collapses in K space. But what is really the telltale signature of something that is a condensate is the fact that below threshold, your emission is, you do an interference experiment and you see that there is no interference pattern. And you go above threshold and you get this beautiful interference pattern with a spatial coherence length extending about 20 microns. And mind you, this experiment is done at room temperature. So like I said, there is nothing that prevents polariton condensation to happen at elevated temperatures, as we have shown here now. The drawback, of course, is that you have to constantly be driving the laser to watch this system. So it's actually a nice platform to do simulations, Hamiltonian simulators, which is what I talked about in my last talk in this workshop, but at room temperature, but especially for studying out of equilibrium phenomena. So this is something that we are pursuing right now, and maybe next year I can give a talk on this topic when we have some results. So again, a lot of work has happened in different phenomena have been observed, different material systems have been studied. I'm not going to read out the whole list. And so when we started work on polaritons in 2D materials back in 2014, we decided that we showed the first time the strong coupling in 2D materials back in 2015, 2014, and then followed it up with a few different experiments, one of which was an electrically driven device that we were able to show. But what we're really interested in now is this idea that we can get nonlinearities at the single photon level. And this is a phenomena called Polariton blockade, which a lot of people people have talked about. There's a lot of interest in this. And the idea is that you're creating really a single photon turnstile. And the basis of this is the following. So you put one photon in, you create one polariton. Now, if you want to create a two polariton state, you need to put two photons in, you create two polaritons. But there is a price you have to pay for creating two polaritons because the polaritons interact with each other. So to create the two polariton state, there is an additional price you pay because of the nonlinearity. And this blue shift of energy that I have here means that the second photon cannot get absorbed inside the system. So this is the idealized hypothetical scenario that I'm talking about. But if you can realize this, what you have is a single photon turnstile, where one photon comes in, it creates a polariton, the next photon comes in, it just goes through because it cannot get absorbed inside the beam. And the result of this is that if you can create this, then if you look at the photons that are coming out of the system, the photons will show some kind of correlation because they know the presence of each other, right? And there has been preliminary evidence of this in these polaritonic systems. 2 years ago, there were these 3 years ago now, these two papers where they showed that when they do G2 or anti-bunching experiment, they showed a small anti-bunching, essentially indicating that you can get correlations in this system. So we've been after this, and we are primarily driven by the idea that in these 2D materials, we might be able to see this. Now, for those really interested in the details, the Polariton, so I told you the penalty that you pay is because of the Polariton interaction. Now, the Polariton interaction arises due to two different cases. One is the Exciton interaction or the exchange interaction. The other is the phase space filling, or in other words, you don't have any more absorbers available and you just fill up the thing. So both these effects become dominant. But if you look at what the result of this, both these effects is, if you sit at this lower polariton, they just blue shift. Okay, so and so the effect that I was telling you in the last slide essentially holds. So we were motivated by this theory paper which claimed that if I go to these large Rydberg states, then I can get increased nonlinearity. And so to prove this, we decided to look at the nonlinearity of the 2D material systems in the excited states. So our goal was very simple. We did not want, we knew we could not do these higher excited states like n equal to 10 and so on. So the question was, the formula that we had asked was, can we see the scaling that one would expect by just going to the next excited state? So let's take 2s, let's take 1s, let's compare the Rydberg states and let's see what happens. And what one sees is that, so this is the structure. This was done by my then graduate student Jay, who's soon going to become a faculty. And he showed that he took 3 layers of this 2D material, sandwiched between boron nitride layers, put it on between 2 mirrors. It's not, I'm making it sound trivial. Making a device like this is not that trivial, especially when you have 3 layers and so on. But thanks to Jay's dedication and drive, we were able to get that. We also had a bunch of collaborators on this work. Theory was primarily led by Thomas Paul's group, the group of Tony Hines for some spectroscopy, and the materials were provided by Jim Hohn's group and Stefan Kennecohen for some of the theory insights as well. So what we see here is that as you cool the system down and as you drive the 2s exciton into the thing, you get strong coupling. But really what the main result of this experiment was to show what happens with nonlinearity. So we pump the system harder and you watch what happens to the polariton branches. And from that, we can extract out effective Rydberg radius that the interaction happens over. and you see the 2s versus 1s. So we are comparing these two systems, and you look at the densities, and you will see that the densities at which you're getting these shifts are almost an order of magnitude smaller than what that is needed for the 1s. In other words, if I look at the interaction strengths of the two, I get a scaling factor of about 4, which is roughly the radius of ratio of the Bohr radius between the two. So this was a nice exercise in proving that going to excited states can give you an enhanced interaction. But the problem is that it's not easy to go beyond 3s. And so, we were struggling with how to do this. And this brought us to another idea, and that is that excitons by themselves are all, they don't have a permanent dipole because they're all in the plane usually in these quantum well systems. But there is another kind of exciton which can be formed where the electron and the hole sit in different layers. And if you can hybridize the two guys, then this essentially results in an effective interaction, which is essentially with a permanent dipole moment, you can get more interaction because now your permanent dipole moment, your Coulomb interaction is much larger. So there was a lot of interest in these kind of dipolar Polariton systems where you can get more interactions. And like I said, the goal here is to increase these interaction strengths so that you can actually go down to the single photon nonlinearities. Now, I just want to point out that the work that we showed with Rydberg, the nonlinearities are such a way that we're still very much in the classical limit. You need about 200 photons to shift by one line width, or slightly more than that. So, but it turns out in 2D materials, there is, if you just take two layer, it's a bilayer. So instead of getting the monolayer limit, you take to the bilayer limit. It turns out in a bilayer molybdenum disulfide, there is an interlayer exciton that gets formed. So this is my layer 1 and this is my layer 2. And you get an exciton that is formed between the two layers where the electron sits in one layer and the hole sits in the other layer. And the hole is actually shared between the two layers in some sense. And what happens then is you get this interlayer exciton, which has got a permanent dipole moment because it's, and in fact, you can apply an electric field and you can move these interlayer excitons. So great. So we now know that you can get excitons with permanent dipole moment. So we actually then showed that you can get strong coupling and all of that. But really what we wanted to do was to prove that these interlayer excitons actually have a higher nonlinearity than my standard A excitons. So this is work led by my postdoc Vishwajit and my then graduate student Mandeep. And what they showed was that if you look at the nonlinearity, and I'm going to just go through this exercise. So we look at the shift of these branches, and what we saw was that there is a contribution from both the phase space filling effect and the effect due to the exciton-exciton exchange interactions and the dipolar interactions. So what we see is that in this case, at low densities, at low Polariton densities, the two become comparable. The two processes get comparable. But what we're really interested in is to ask the question, what happens, how much shift do we get in these line widths if you put a certain number of photons? What we really want is one line width shift for one photon. That's our ultimate goal. But let's see where we are. So you will see that this is the interlayer, this is the intralayer, which is the A exciton. And you will see that at these very low densities, you need about 100 polaritons to shift by a line width. So again, we're still in the classical limit. We haven't got to the quantum limit of few photons. But we do think there is a way here, because in this particular experiment, we haven't even applied a voltage. If you apply a bias, you can get permanent dipoles in the system, and with permanent dipoles, you can get a large nonlinear response. So I think this is where we are going towards. We are trying to get larger nonlinear response from these systems. How much time do I have?
You still have another half hour.
Okay. So then let's skip topics a little bit. So far, all the nonlinearity work I talked about was in the weak pump limit. Now I'm going to talk about the high pump limit. So this is second harmonic generation. So if you take your classical nonlinear optics textbook, like Boyd or something like that, one of the first things you learn is that you need a system with broken inversion symmetry to get second harmonic generation. Of course, you can get surface second harmonic on the surface of materials and so on. So if you take these 2D materials, they have some very interesting property, which is that in the monolayer limit, in most of these materials that I was just talking about, the inversion symmetry is broken. So you get a nice second harmonic signal. You go to the 2-layer system, then they're on top of each other, and you don't get second harmonic signal. In fact, that is shown nicely here. You can see that as I increase the layer number, I go from 1 layer to 2 layers to 1 layer to 2 layers, and it keeps dropping. And then by the time you get to bulk, you usually don't get any second harmonic signal because there is no broken inversion symmetry there. So what we did was we took a bulk material. So this is your bulk material. So this is some 2D material. And it turns out that because these materials absorb light so much, and because they're around the exciton resonance, they have a very large refractive index. What happens is light gets trapped by itself. You don't need a cavity. You just take a bulk of this material. It's not a direct band gap. Nevertheless, you can trap light inside the system. They've got a very high refractive index. So we take this material, we create this high refractive index material, and then we put it on top of a mirror here. We have an air gap and all of that. And you can see that you can get nice strong coupling just between the light that is coupled inside and the excitons that are inside the system. So you don't need a cavity for this particular experiment. But the most interesting or the intriguing aspect of this structure was we found that if I just took this bulk material of some random thickness and you did second harmonic generation, there's no signal, barely anything in this signal. But then I go to this Polariton system and then I pump here. So it's around 800 nanometers wavelength. And I suddenly get a lot of second harmonic signal. Okay. And so a non-existent second harmonic signal suddenly becomes existent, and it's actually several orders of magnitude higher than what the bulk material does. And also you could tune it depending on whether you're in resonance with the Polariton or not. So, and of course, you have a quadratic dependence, so we know it's second harmonic that you see. We also saw that it obeys the crystal geometry. So you can rotate the crystal and you can see that it has this flower-like pattern, which indicates that it is not a surface effect. It's actually coming from the bulk of the material. And in fact, in the at the low pump power limit, you actually see that the second harmonic is greater than from the bulk. This Polariton system is greater than even the monolayer. So are we really relaxing selection rules for nonlinear optics via strong coupling? So that's really the question we wanted to understand, and why is this happening? Again, this is just the power dependence. So to do this, we collaborated with a group of Andrea Alu, who is a colleague of mine here and at CUNY, and we looked at what is happening to the polarization that you're generating inside the system. So they did their calculation, and then here is what they see. So if you take the bilayer system on its own, it's got a very weak nonlinear response. And then if you take the bulk tungsten diselenide on SiO2, it's like 10 to the minus 2 or something like that, or a few 10 to the minus 3. But the moment you go into the Polariton system, you suddenly boost up by 2 orders of magnitude this nonlinear response. Of course, it's at a resonant phenomena. It only happens where there is a Polariton system. And so this kind of explains, this shows that the theory at least is able to reproduce the experimental result. So again, work led by my graduate student Resland and my other graduate student Mandeep. So oops, what's happening here? So to understand what's going on, we should look at the electromagnetic field. And nonlinear optics is all about phase space, phase matching and so on. And it turns out that at the within this thick material, 140 nanometers, there is a small region where the polarizations created in each layer is not cancelled by the next layer. So in every other layer, it's usually cancelled. One points up, the other one points down. But there is a few layers here where this condition is not satisfied, and where you get net or effectively some nonlinear response. So although the material is 140 nanometers, the actual nonlinear response is coming from a bulk of the material which is sitting inside, which is only about 30 nanometers. But that is coming about because of the way the electromagnetic field is sitting inside the structure. So I'm not saying that I've violated anything that has been written in any of the nonlinear optics textbooks. The only take-home message from this experiment is that you could take a centrosymmetric material and still get nonlinearity if you can design your electromagnetic field appropriately, where you break the symmetry not by the structure itself, but by the way the field is sitting inside the structure. And with these 2D materials, it's easier to do it because these layers then act almost independently and the polarization created in each layer is different. So that's the take-home message. So the textbooks still hold, except the only take-home thing is that you need to worry about how the field is localized inside the structure. And through this, you can actually break some of these rules if needed. Okay, so moving on, other ideas of increasing nonlinearity, strain. So, we usually don't like strain in these materials in semiconductors, but it turns out in 2D materials, again, strain is a very beautiful tool to play with. And so here was an experiment that we started just when the pandemic started and labs were shut down. So my postdoc Florian flew back to Germany where labs were still working, and he collaborated with the group of Alexei Chernikov and his student Jonas, and did this really careful experiment where he took a wire. It's a nanowire of gallium arsenide. It's only 90 nanometers in diameter, and he draped this 2D material on top of it. The 2D material drapes around like a tablecloth on top, and it introduces strain. So this is an atomic force microscope image which shows how the 2D material wraps around. What strain does is it effectively creates a potential minima for the carriers inside the system. And you can see that clearly here. So this is a map where I'm going from one end of this structure over the wire and down here. And you will see that as I go over the wire, all the energies of the excitons get redshifted. So redshift meaning that I've got a lower potential minima there. And then I go back and then everything gets. This step is only caused because I'm only going one way. And that is the reason I'm seeing this step. It has nothing to do. So if I sweep the other way, I would have seen a step on this side. So you will see that all the excitonic species in the system are all redshifted. But again, the main message is strain introduce a potential minima. And essentially now we ask the question, can I make this kind of a potential minima act like a guide for excitons to flow? So that's in fact what we did. We looked at the propagation along the wire, perpendicular to the wire, and we looked at what is the diffusion. And you will see that the diffusion along the wire is about what you would get from a regular monolayer material, but perpendicular to the wire, the thing doesn't move. So you've actually localized the excitons in the perpendicular to the wires, and it only propagates along the wires. And you can actually model this very easily with a drift diffusion model. Everything agrees. And why are we interested in this? So right now we are in this regime where even though the nanowire that we are using is only 90 nanometers, because of the way the 2D material tends around this nanowire, you get, the effective length is about 1000 nanometers. But if I can push this into into a 2D true 1D limit, then I can start seeing quantized levels in the system. And this is not easy purely due to experimental limitations, but it'll be a fascinating area to look at once we can get to this limit. But in the meantime, what we have done is we've again gone back to the Polariton physics and asked the question, since we know excitons prefer to come to this minima, can I have an effective nonlinearity that is higher? And so what we've done is we've created a cavity with pillars where we get maximum field here. And you can see the light only coupling happens on top of these pillars or in these ridges. So this is an atomic force microscope image that shows how the 2D material is wrapped around these pillars. And the effective, the end result is that the blue shift or the nonlinear response is much more enhanced on the strain system. So there's a nice exercise in where strain is used to localize carriers. And by using that, you get an effective nonlinearity, which is larger than what you would get if it was unstrained. Okay, so in the last 15 minutes or so, I want to switch gears. So everything I talked about right now was on excitons in 2D materials in 2D semiconductors of transition metal dichalcogenides. Lately, there has been a lot of interest in asking the question of whether if I take excitons or carriers in correlated materials. So the first, I mean, of course, superconductivity is the first thing that comes to everyone's mind. And you put it inside a cavity. Can you modify the properties of the superconductor? And the naive or the very simplistic way of thinking about this is, if you think of if a superconductivity in a given material is arising out of electron-phonon coupling, and if I can engineer this electron-phonon coupling somehow through this cavity-mediated interaction, then can that affect my superconducting transition temperature, for example? So the theorists have got very excited about this topic. It's really fascinating. Of course, superconductivity is not the only material. There are a whole slew of other phenomena, phase transition, and so on. So the bigger question in the field is, can you affect phenomena like phase transitions or other collective phenomena or coming from correlations in the material through cavity coupling these material excitations to cavity photons? And so in that vein, one of the first things that we have done recently is we've looked at a material called nickel phosphorus trisulfide. Don't worry about what this material is, but this material is not a semiconductor. It's actually an antiferromagnetic material. It's actually a correlated insulating material, and it turns out this material also hosts excitons. And this was a paper that came in 2020 where they showed that these excitons are they are coherent excitons. Their line widths are on the order of 300 micro eV, so extremely narrow, and they emit light with a polarization that is perpendicular to the spin chains inside this material. So these are nickel atoms, and then these are the purple ones are phosphorus atoms, and then the sulfur ones are the ones shown in red. And the intriguing thing about this material is these materials, because they have these spin chains, they host magnons or spin waves, and the spin waves have been studied in the past. You can see them with Raman experiments. You can see them with far infrared measurements or RIX type measurement where they see these magnon bands. And there have been some experiments where they've shown that you can drive these excitons, which are indivisible. So that's sitting here. And you can watch these magnons oscillate in the terahertz. So that's also very intriguing, that you can actually drive the excitons, drive the magnons by driving the excitons itself. So we went ahead and made some of these materials inside cavities. This is the work, and you will see that you can get easily strong coupling and all of that. But really, what we wanted to understand in the system was more not about showing strong coupling, but can we use the strong coupling as a way to understand the nature of the excitons inside the system? Why are they so coherent? Why are they so narrow? Why are they tightly bound? And why do they have weak oscillator? Their oscillator strength is not very weak. The other interesting thing is, as I increase the temperature and I go past what is called the Neal temperature, where antiferromagnetism disappears, then this whole strong coupling and excitons and everything disappears as well. We studied the nonlinear response of this material, and we see that it's not easy to for these polaritons in this system to interact. So what this told us is that these excitons are probably tightly bound, but they have a very weak oscillator strength. And the only explanation for that we can come up with is that you have the electron sitting in one of these nickel atoms, and the hole is sitting in one of these sulfur atoms, and or it's shared between two sulfur atoms. At least there are two options there in the two sulfur atoms. And the result is that they're very close to each other, the electron and the hole, but the wave function overlap is not large enough that you get a good oscillator strength. So that's our current understanding. It's still an open debate. And so we were able to show the strong coupling. And in fact, this paper just got accepted and should be coming out soon, where we showed that we can get strong coupling in the system, but more importantly, we were able to shed some light on the nature of excitons. So here is an example where we took a correlated material. We did not understand what is the nature of the excitons much. And then we used strong coupling as a means to study those things, because they have coupled to photons, we can interact, we can probe them more easily, and we were able to understand a little bit more about the nature of the excitons. Again, this work led by Florian and my grad student Reslan. So, but one other motivation we had when we started this work was to ask whether by manipulating the excitons or strong coupling to excitons, can I affect the magnons inside the system? But that's something that we were not able to prove in this work, because it's not clear to us that the excitons are strongly coupled to the magnons in the first place. So because of that reason, we started looking at other materials. And one of the materials we have recently started working with is chromium sulfur bromide, which is another van der Waals magnet. They're highly anisotropic. So if you exfoliate it, it becomes like a strong, essentially a strip. And if you look at the band structure, the band structure is shown here. And this is taken from a recent collaboration of ours. So it's a semiconductor with a band gap of about 1.5 eV. So it's not a correlated material like I talked about earlier. It's an anti-ferromagnet below 130 Kelvin. And the coupling is between the layers, it's anti-ferromagnetic, as you can see here. And between the layers, it's anti-ferromagnetic. Within the layer, it's ferromagnetic. So everything is pointing in the same direction. And these are air stable as well. And you get nice excitonic features. Of course, you need to go to low temperatures. And so we made a mirror where the bottom mirror is a Bragg mirror. You have the material here, and you have a top mirror sitting on top. And you will see the Polariton branches. All of that is straightforward. You get strong coupling, great. But what we are really interested in is what happens to this material in the presence of magnetic field. So if you apply a magnetic field, all the spins in one layer start aligning, trying to rotate. These guys also start rotating. I increase the field, and then eventually at some large field, everything becomes pointing in the same direction, and you reach the saturation field where everything becomes ferromagnetic. So again, just to give an idea, you start with something which is in the layer, it is ferromagnetic, between the layers anti-ferromagnetic. You start increasing the field, and you slowly reach this regime where everything is pointing in the same direction, or you become ferromagnetic material. So clearly the excitons in this material correlate with the magnetic order. And if you look at the reflectance, the excitons, so you start with zero field and you start changing the thing, everything redshifts, but it also saturates out, where it becomes, in this case, ferromagnetic pointing down, ferromagnetic pointing up, at zero field, anti-ferromagnetic coupling. So we just want to, so what this proves is that you can create magnetically coupled exciton polaritons. I mean, that's really the key here. And I'm going to skip this slide and just point out that you can actually see exciton-magnon coupling. You can see long-range propagation of magnons in these systems. And so you could envision these for coherent spin transport. So I think with that, I want to conclude and leave some time for questions by pointing out that the strong light matter coupling and the formation of these quasi-particles called polaritons is a nice platform to study nonlinear optics in the weak pump limit. We showed the use of Rydberg polaritons, the interlayer polaritons in these 2D materials, and also this idea of strain, and then more recently this idea of using correlated materials in cavities and being able to either probe them or affect their overall electronic response. 2D materials also becomes a really nice platform to study these things because, as I said, you have a whole class of materials ranging from superconducting materials to insulators to metals and semi-metals and semiconductors. So you can study a wide variety of phenomena, especially if you're interested in things like cavity QED, where you want to modify different properties. I must say all of this work is possible only because of these wonderful students in the group. And a lot of the work on ferromagnet, these last thing that I talked about was led by Florian and Resland, who's here. The work on interlayer excitons led by Vishwajit and Mandeep, who are shown here. And the others, I didn't report any of the work that is shown here. The organic polariton condensates led by Sitakant, who's a postdoc in my group, who came to my group as a chemist. He had done organic chemistry PhD from IIT Madras, but decided to join my group eventually, and now He's a hardcore quantum optics guy with chemistry background, making him really unique. So we have people from all over and with different backgrounds, and I'm always looking for motivated students and postdocs to join the group. And I leave you with some of the recent publications that have come out from the group, and I'm happy to take any questions. And thank you all.
Yeah, this was a very, informative and wonderful lecture with so many exciting new results. And the floor is open to questions. If anybody from the participants have questions, please.
Let me start. Vinod, can I ask you a question?
Sure.
So you mentioned about this context of exciton, spin half kind of anomalous excitations in spin one object. That paper, 1993 paper which you referred.
Yes.
There was something like spin half in a spin one kind of thing in that paper.
Which one are you talking about?
I'm talking about, if you show me that paper, in the context of that Nature paper, 2000, this 2020 paper.
This one?
That's right. Yeah. After that, just go to the next page. Yeah, this one.
Yes. This one, right?
Spin half-like anomalies.
Yes.
So spin half-like anomaly, what does it imply? That there are excitons of or excitations with spin half kind of statistics or spin by half value?
Well, so this paper was the main reason I put this paper up was this was the paper, but this was one of the first studies of this 2 Magnon-like scattering that happens in these systems. So this whole class of materials like nickel phosphorus, manganese phosphorus, they all have this Magnon sideband, where the electronic excitations couple to the Magnons, and you see a Magnon sideband, and you will see that this Magnon sideband is in this case about 500 inverse centimeter or 600 inverse centimeter. And that the purpose of this paper was more about showing the presence of these 2 Magnon sidebands with Raman scattering. And then they identified this as this particular transition. So not just phonons, they looked at the Magnons as well. So these peaks that you're seeing here are the phonons. And then this broad peak that we're seeing is the Magnon peak. And so in Raman, you can't directly excite the Magnon. You need to use a 2-photon excitation type process. So that it's the 2 Magnon excitation that we are seeing here. So that was this result. But the reason I wanted to point out was that these materials were studied before and people had seen the Magnons. But what for some reason everyone had missed was the presence of these excitons inside this material, which happened, and the fact that these excitations seem to be correlated with the Magnons because the polarization of the light emission is always perpendicular to the spin chain.
Oh, okay.
Yeah. So in fact, you will see here in our results, for example, they're beautifully linearly polarized. And this linear polarization is always perpendicular to the spin chains inside the system.
Thank you. Yeah.
Okay. You really are doing engineering the material to dance to your
with light. That's the most important thing. Light and a cavity. That's all we use. Yeah.
Very exciting. And also, the pictures, those FEM and all these pictures, they look so clean. How is that?
Well, you just need good students, Prasanna. Good dedicated students, and and then the rest is easy. Yeah.
The experimental, pictures, they are looking so clean, and it's really fascinating to be able to do such clean experiments with such.
Yeah, some of these are like this one, for example, is a low temperature experiment. But yes, this data is, even though it's from my group, I must say it's one of the cleanest strong coupling data I've seen, in where you're coupling to all these excitons at the same time. And so this was work done by Bishwajit, who is a postdoc in my group. Bishwajit did his postdoc at TIFR.
Okay.
Yeah. And
good. Prashanta? You are
Well, if there is no more question, can I ask one more question? I see.
Please.
Typically in